Okay, so today is hybridization. I guess your homework will be those last two packets of pages that you have. So what hybridization is a mixing of our atomic orbitals. So mix our atomic orbitals to make new hybrid of new energy, new hybrid orbitals of new energy and shape that are suitable for bonding. So if you will look at, we have this s orbital, okay, and that's around the central atom. And then we have these p orbitals over here. So what happens is the s and the p's will come together and they will make some new hybrids. So we have, if we were to make this hybrid, we have the one s orbital, and then we have the 3p. So what happens is the s and the p's come together, and we end up getting an sp orbital. We end up getting 3 sp3 orbitals. So we're using all three of those p's, and we're using that s. So if we have an s, I'm going to talk about that. Or those the other ones? Yes, sorry. 4 s and p orbitals, sp3. So if you think about this, you have the s orbital. How many is that? That's 1. You have the 3p orbitals. That's a total of 4 orbitals, right? So what happens is they come together and they hybridize to make this new orbital, and we call it the sp3. And so 4 orbitals, 1, 2, 3, 4. They hybridize, and we get the sp3, which contains this. If I count the p3, that's 3 plus 1 is 4. So it's 4 orbitals making this new orbital. So this is how we get more than those couple of atoms around the central atom. So let's take a look at. So that's to create the 4 areas. Now, if we just want to have 3 areas around our central atom, what we're going to do is we are going to utilize an S and then 2 of the P's, and that will give us 3 areas. And so we will have sp2, we'll have 3 sp2s and 1 p orbital, which is not changed. So if I'm looking at this hybridized, what we have here is we have these clear or these blank ones, and those are our 3 sp2 orbitals. And the angle between those is 120. So if I go back to the last slide, then each one of these here is an sp3. And the bond angle between those, since there's 4 of them, would be 109.5. Okay. If we only wanted 2 areas around there, then we're going to use one S and one of the P's. And that's going to give me 2 SP's, orbitals, hybridized orbitals, and then 2 unchanged p orbitals. And then you have your sp and your sp. What if you needed 5? What if you had to create 5 areas? We can't get 4 p's. So if we needed 5 areas, we would use 1 s, we would use our 3 p's, and then we would use 1 of our d's. So that would be a sp3d. Okay? So what I want you to do is go back to the slide that has our the big chart that you have to memorize. That has the hybridization there. Right here. So if we're linear, so it would be an SP hybridization because we need 2 areas. If we had 3 areas for our trigonal, or our trigonal planar, it would be SP2 for both of those. Now if we added another area so that we have our, are we at tetrahedral? 4 areas, we would be SP, or 3 areas. Wait. Yes, SP3. So all of our 4 areas are SP3 hybridized. If we have 5 areas, we are going to be SP3D hybridized. And if you have 6 areas, then you are SP3D2 hybridized. So you are expected to be able to look at the bonds and know what the hybridization is. Is it SP, SP2, SP3, whatever?
Why doesn't it change for the banks and others? Because that
There's still electronic areas there.
Yes. Wouldn't it be like when we have these right here?
No, because you would have that would be when you're SP, where you would have those ones that aren't being used. But those areas of electron, if it's expanded and you have those electron densities, wherever those electron densities are, that is going to be hybridized. Okay. Okay. So let's go back and let's talk about our next slide. All right. So we have sigma bonds. That is a single bond. We have free rotation. And it's characterized by a head-on-head overlap. So here is a sigma bond. We're going to draw this here in a minute. Please pay attention. This is a sigma bond right here in the center of this. That is just one single bond. We have a head-on-head overlap of those orbitals. Now, if you were to double bond here, so what happens is we have a sigma bond, but then we have a pi bond. So we have the overlap of those p orbitals, and these do not rotate. There's no rotation in there. So we can have the rotation in the F or the S, but not in the P's. And you can only do that if you have those empty p bond or empty p orbitals. And then here would be a triple bond, and here you have your S, your sigma, and then you have a pi and a pi.
Why does it have?
Okay, so this is the sigma, and then we have the two pi's here. And those are the overlapping of those orbitals, those unused p orbitals are overlapping. Okay. So a single bond is just a sigma, double bond is a sigma pi, triple bond is sigma pi pi. So let's draw ethane. Ethane, the molecule ethane, it is a C, C, and then we have 3 H's on it, on each C. So if we were to look at the hybridization, what happens is we have our C bonds, and how many areas of bonding do we have around each C? We have 4. So that means we have an sp3 orbital. We have 4 sp3 orbitals around each C. And then they are all bonded to hydrogens, and that is just going to be an s orbital that bonds it to a hydrogen, each one of those. So this bond right here, these overlapping of the sp3s is our sigma bond. We have an overlapping here of our S and our sp3 from our H, from our hydrogens, and that is a sigma bond. So how many total sigma bonds do we have? Any single bond is a sigma bond. So how many sigma bonds do we have? So we have 7 sigma bonds. Okay, and so here, if you're looking at this model, you have your sp3, your hybridization, and then you have the s orbital bonding to that. Any questions on that? Okay, so then let's draw ethene. So ethene, what we're going to do is we're going to take ethane and place a double bond in there. So now what we're going to have is, hold on, we have C, C, H, H. So now we take our C's, and we have how many areas of hybridization, how many areas of bonding?
4
areas. There's only 3 areas of bonding, right? So we have an sp2, an sp2, and an sp2 on this one. And then we do the same thing to the C, where we have an sp2, an sp2, and an sp2 here. And then, of course, you have your S's for each hydrogen out here. And then you have your p bonds, the p bonds that aren't being used. So, or p orbitals. So we have a p orbital here and a p orbital here. Why? Huh? Because we only have 3 areas of bonding. Oh, wait. So this is the last p orbital. This is kind of the same thing right here. That's one of the p orbitals. And then you have one p orbital from the C. And what happens is these guys have that overlap, no rotation. And that is your pi bond. So how many sigma bonds do we have in ethene? 5 sigma bonds. And how many pi bonds do we have? It's 1 pi bond. Okay? What? Might have to go do some reading. You can't read?
Wow.
Sounds like a personal problem.
It's in his 504.
All right, next is ethyne. So ethyne, what we do is we're going to remove 2 hydrogens, and we end up getting a triple bond C. So we have C, triple bond, C, and then we have an H on either side. So now when we look at this, how many areas of electron density do we have around the C? We just have 2, so we have our SP and our SP. And then we have our SP here and our SP here. And then we left over is we have this p orbital. I guess I could draw that in a different color. We have this p orbital and this p orbital. And then on the C we have a p orbital and a p orbital. And then what happens is now you've got this overlap of these. That's your 1 pi bond. And then you have the overlap of these, which is your 2nd pi bond. So we can say that how many, and then you have your S with your hydrogen. So how many sigma bonds do we have here? We have 3 sigmas and how many pi's? 2 pi. So once we can start drawing it, it might look a little bit easier. Everybody good with just drawing before I go to the next slide? Okay, so here we go. I have IF2 minus. So it wants to know the hybridization, geometry, and the geometry on the central atom. So if I have IF2, so we do with a -1, so needed, available, shared, 3 times 8 is 24. Available is 22, so we have 2 shared. So it's expanded octet. So we have iodine, fluorine, fluorine. I'm not going to fill out those fluorines, but right now we have 16 being used. 16, 17, 18, 19, 20, 21, 22. And then your brackets. So, what's the hybridization? How many areas are there around I? How many areas of electrons are there? 5. So that means it has to be S, that's 1, plus my 3 P's, so that's a total of 4, plus a D. That is your hybridization. So what would the angles be?
Isn't there like 2 minus 30
It's just a 180, right?
Yeah, it's 180.
And the polarity is nonpolar. What's the shape? Linear, but linear what? Trigonal, bipyramid. Okay, so all you have to do is really just look at those electron areas and see how many you're looking at. So if I go to OSF4, so I have needed, available, shared. I have 48 needed, 40 available, 4. So my problem is now that this is going to be in expanded octet, I am just going to draw my atoms and look at it. And so how many areas of density, electron density, do we have around it? 5. So the hybridization is what? sp3d. What's the shape? Bipyramidal, bipyramidal. Trigonal, bipyramidal. And what's the polarity?
Oh, it is.
What makes it polar? There's no lone pairs. That oxygen makes it polar. Because it's not symmetrical. And how many?
So if there were six things on the S and 2 of them were O's,
It'd be polar.
that'd be polar.
Mm-hmm. Because those fluorines are more electronegative, so they're going to be pulling them towards it. Okay, SiF6. SiF6 with a -2 charge. SiF6 minus 2. So Si is in the middle. I'm going to draw my 6 F's around it. With a -2 charge. I need 48 electrons, and right now there's 48. So what's the hybridization? How many areas of electron density? sp3d2. And what is the shape? Octahedral, octahedral. Polarity? Nonpolar. And then if I were to draw this one, we've already drawn it, but let's draw it again. So what's the HCCH? What's the hybridization? 2 areas, so it is SP. The shape is what, Andrew?
SP, the shape is linear.
Linear, and the polarity is nonpolar.
That was not
Get this wrong.
No, that wasn't the easiest one. I got lucky.
That was a good answer.
Geometry.
Good job, buddy.
And which one?
Represent only planets.
Right. Yeah, actually, that's still tricky. Yeah, I get that.
It's just linear. Because there's only 2 angles. There's no
Type
lone
it
pairs.
to me, and I was just, okay, I just slipped it in my bag. I got the engineering. I was like, what are these?
Okay, so let's do some of these next ones. These are going to be similar to what you'll see on your test. Okay. So, consider the Lewis structure for glycine. Says, what are the approximate bond angles about each of the 2 carbon atoms? And what are the hybridizations of the orbitals on each of them? So first of all, let's talk about the bond angles on each of the 2 carbon atoms. So for this carbon atom, how many areas do we have around it? 4. So what's its hybridization? sp3. And what are the bond angles? 109.5. All right, let's take a look at your other C. How many areas of density do we have it? 3. So the hybridization is sp2, and the bond angles are 120. Questions on that? All right. The next one says, what are the hybridizations of the orbitals on the 2 oxygens and the nitrogen and those bond angles? So let's do this oxygen first. What's the hybridization? How many areas of electrons on it? 1, 2, 3. There's 4 lone pairs out there. Or 2 lone pairs, sorry. So there's a total of 1, 2, 3 areas of electrons. So what's the hybridization? So if you don't see it, right here is an electron, right here, and right here. So it is sp2.
So the double bond.
The double bond is 1 area of electron density. Okay?
And that would be
Linear. There's really not an angle right there, so we wouldn't worry about that. Let's go to the other oxygen. The other oxygen has how many electron areas? 4, so it is sp3. What is the bond angle?
It's linear.
4 areas around it.
2 on each.
109, less than 109.5. Huh? It's tetrahedral. Yeah, so it would be less than 109.5. And then the next one, N. What's around N? So if we were to really look at this, what's happening in N is we have an H here and we have an H here. So how many areas of electron density around N? 4. So it is what? sp3, and the bond angle is less than 109.5. How many sigmas, how many pi's? Did you count the 2 H's on N?
I didn't count. I guess 9. Did you count the double bond as a sigma number?
Yes. So it's 9 sigmas, and how many pi's do we have? Just one. Everybody good? All right, let's go to the next one. Indicate hybridization and bond angle about each of the central atoms in the molecule shown below. So we have 4 central atoms here. Thank you. Thank you. I need to know the hybridization and the angle. So let's just go in order. So this very first one, what's the hybridization around this first C? sp3, and the bond angle is 109.5. Okay, what about that? The next C? sp2, and the angle is 120. The next C is what? sp3, and the bond angle is 109.5, and the N, sp3, no D, and the bond angle is less than 109.5. How many sigmas, how many pi's? 8 sigmas? 11 sigma, and how many pi's?
9%.
The double bond has 1.
1 pi.
How did you know? I'm sorry, I have to use it because it's bad. I've used at least 15 years.
How do I know it's a pi? A double bond is made of 1 sigma, 1 pi.
Oh, any double bond?
Any double bond made of 1 sigma, 1 pi. Any triple bond is 1 sigma, 2 pi's. Any questions on that? All right, that's it. Molecular orbital theory is out of there.